Okay, so now we're going to be looking at part 2 for chapter 3. And in part 2, what we're going to do is we're going to say, hey, what would happen if we start adding things in columns? So when we're doing substitution method, we're trying to identify or kind of eliminate or say one variable equals this. But what if none of the equations look nice for having one variable equal another value? So what we're going to do instead is we're going to say, what if we just looked at our x values? What if we just looked, and I know this is kind of hard, at our y values? What if we just looked here at our constants? And what if I just added those together? So looking at my x values, adding them together would be 0 x's, a positive 3x and a negative 3x, 0 x's. For my y's, we'd get 2 y's, because a negative 2y and a positive 4y is 2y. And then for the constants, we would get 70. 42 and 28 is 70. And so what we have is we really have the equation here. We can kind of say, well, let's ignore our 0x. So we have an equation that 2y equals 70. Well, if 2y equals 70, I can divide both sides by 2, and y must equal 35. Okay, y equals 35. Knowing that, let's then look and say, well, we know what y is. If we can look at our original equations, I'm going to get rid of all the extra stuff I had here. In my original equation, I can pick either one. So I'm going to pick this first one and say, well, I know here that negative 3x minus 2y equals 42. And I just found out that y really isn't y, but it's really here a 35. So I can put in 35 for y, because I found out that at y equals 35, it's going to solve both of these. So now my problem is really negative 3x minus, let's see what 2 times 35 is, sorry, it's 70. And then that equals 42. Well, I'm going to add 70 to both sides. Let's see if we can solve this. Adding 70 to both sides, I get that negative 3x equals 112. Now I'm going to divide both sides by a negative 3. I need a little bit more space, don't I, here? Let's see if I can get, there we go. All right. Well, now x equals, this would be negative 3, and it would be, are we at 37 point, where are we? I got to do it this way, guys, sorry. We'll ignore the fact that we have 3, it'd be 9, 22, 7, and it would be 3, 9, 1, 0.3 repeating, so 37.3 repeating. All right, so what we found is the solution to this is going to be the ordered pair negative 37 and a third, or 37.3 repeating, 35, okay? So that is how you solve these to work it out, to say, okay, I can solve for one value. Now let's look at another example. Now in this example, if I added my columns, it wouldn't work out as nice as it did in the last one, because if I added this column, the x column, I'd get negative 1x. If I added the y column, I'd get negative 3y. And if I added my constant column, I'd get negative 12. That doesn't help me much, all right? In fact, it doesn't help me at all. I still have two unknowns, and nothing kind of became a 0 or fell out. Well, I can manipulate an equation, all right? Manipulating an equation means multiplying the entire equation by the same value, each and every term, and then kind of changing it. So in this case, if I multiplied each and every term by a 2 here, okay? So I'm going to take 2 times the x, 2 times the 3y, and 2 times the 12. All right, that's what I'd get. 2x plus 6y equals 24. And then at the same time, I'm just going to copy down what I have here. I'm just going to copy it so they're one underneath each other. Negative 2x, negative 6y equals negative 24. Now if I add those two, what I would get is I'd get 0 x's plus 0 y's equal 0. So in fact, I get 0 equals 0. Well, this is a unique case. I kind of should have showed you one in between here, and I'll show you another one here in a minute. But this is a unique case. Whenever you get a true statement, all right, whenever you get a true statement, the answer is all real real numbers. Okay. All right. Infinite solutions. Infinite, yep, I think I got that right. Solutions. All right, which means what? Well, when we originally were graphing these, all right, we were talking about how you are, what they look like in graphing. And there's three possibilities when you're graphing two lines. One possibility is one line goes like this, and they cross in exactly one point. So one possibility is they cross in exactly one point. And that is when you get like a single point, all right? You get an x equals something and a y equals something. But then they have another possibility. Another possibility is that you have a line here, and that the other line is right on top of the first line. And it kind of looks like you can kind of see the black line there, but the blue is right on top of it. In this case, they're kind of piggyback, and in this case, there's infinite solutions, and we kind of use that infinite sign, infinite solutions. Or no matter what you put in for an x and a y, you're going to get a solution, so you could say all real solutions. So we can do this for all real solutions. There's one last possibility, and that is you get parallel lines. And in that case, there are no solutions. So you can write no solutions. A lot of times what we do is the solution does not exist, all right? And this happens, just so you know, when you have a false statement at the end. Remember this one happened when we had a true statement? True statement, you know, and then for our true statement, we had 0 equals 0. It could have been 7 equals 7. It could have been anything equal to self. In the end, if you have a false statement, like one that can't possibly happen, like 7 equals 14, that's when you have parallel lines and no solution, okay? In this one, we're going to have one solution like, oh, x equals 7, and then we'll be able to solve it later for like x equals 4. So that's how we know it has a single point here that has a solution. We know it has infinite solutions if you get down to a point where you get just a true statement, a does statement. Yeah, 0 does equal 0, 7 equals 7. Or if you have a false statement, it's no solution, and we have parallel lines. So let's look at some more examples. And here is one where I'm just saying, you know what? Choose what works best for you. Choose what kind of intuitively sounds good. In 17, what I would think intuitively, you could go with substitution. But I'm going to say that if I just multiplied, I want to show you an example of an elimination where it actually works out to have a solution. So I want to say that I can multiply my second equation here by a positive 5. And I would do that, I'd multiply each and every term by the positive 5, and I'd get 5x plus 5y equals negative 20. So you notice I multiplied each and every term here by the 5. Now to remind you, in front of it, and I like to have them right on top of each other, I'm just copying this down. All right, so I'm just going to copy down what I had there. I'm just going to copy it. Okay, so now what I can do is I can add my two equations, add the columns. The x columns become a 0, and I usually don't even write those down because it's a 0 and I write down a 0. My y columns become 7y. And my constants become a negative 7. Well, in this equation, then, it follows that y must equal a negative 1 because only 7 times a negative 1 gives me a negative 7. Then what you do with that information is you take it back. Almost always I'll take it to the first equation, although it'd be even easier to take it to the second equation here. The second equation says x plus some y equals negative 4. Well, I know my y is already a negative 1, so it's like x plus a negative 1 equals a negative 4. What plus a negative 1 equals a negative 4? Another way we could do this is we could add 1 to both sides. Add 1. So now I'm getting a solution that x must equal a negative 3. So my overall solution to this, and I'll put it down here, is the point negative 3, negative 1. Okay? That's my solution. Oh, it kind of came down, looked like 11. Sorry, I had a issue there. All right, negative 3, negative 1 is my solution. Now let's look at 18. Now 18 really lends itself well to the substitution method. Y equals x minus 7. That I can substitute in for this y. Y can be replaced with an x minus 7. So I'm going to go ahead and do that. 2x minus 2 times y. Well, y is going to be replaced with x minus 7. That's what they told me here, that this y is really the same thing as an x minus 7. equals 14. I'm going to do distributive property here because now I have an equation with just one variable. 2x minus 2 times x, and then minus 2 times minus 7 is plus 14 equals 14. Combine these two terms and I get 2x minus 2x is a 0. So I'm left with 14 equals 14. Now you remind yourself, I've said what happens when you get like a true statement like this. Our answer is there's infinite solutions. Those are piggyback lines. Okay. This one I really could go either way. I could solve it either for x or y and use substitution, or I can multiply it out and use elimination. I don't think it really matters. Let me go ahead and use substitution since I already used elimination here. All right, so I'm going to take this second equation right here. I'm going to say, well, if x plus y equals negative 2, then x must equal a negative y minus 2. Okay, so I just subtracted y from both sides. Well, the x here then can be replaced with negative y minus 2. So I'm going to do that. 2 times x, 2 times negative y minus 2 plus 4y equals negative 28. I'm going to do distributive property here, multiply out. So 2 times a negative y would be negative 2y. 2 times a negative 2 is negative 4 plus 4y equals negative 28. I'm going to combine like terms now. I'm going to combine my 2y and my 4y, and I get 2y, because it's a negative 2y over here, minus 4 equals negative 28. And then I'm going to solve it real quick. Add 4 plus 4, 2y equals negative 24. Divide both sides by a negative, or a positive 2. This is a positive 2, sorry. And I get y equals negative 12. So what I know now is my ordered pair solution is that the y is negative 12. Well, I knew up here from my green that x is negative y minus 2. So the negative of a negative 12 is 12 minus 2, x is 10. So I can say here really my answer in the end was 10, negative 2. So this is a really important idea, is that you need to know how to use the elimination and the substitution method. Now the other thing we did is we started talking about this chapter, we talked about how do we graph two lines, but now we're going to talk about how do we graph two inequalities. So we're going to start with graphing the inequality y is greater than x, greater than or equal to x. Well, what I'm going to see that is, in my head, I see this as y is greater than or equal to x plus 1, or not plus 1, sorry, plus 0. I can't just add a 1, but I can just say, hey, we really have like a plus 0. We usually don't write down plus 0. So now I have that plus 0. So I'm going to think of myself, how can I graph it? So we remind ourselves that's going to be in green. I'm going to start with my starting point, which is where does it cross the x-axis? And it crosses here at 0. Then I'm going to go and say, what is my up and over? What is my slope? And it's a 1 and a 1. So for every 1 up, 1 over. All right, 1 up, 1 over, 1 up, 1 over. Hey, this is the way this looks. Now, for every part of this line, my y is greater or equal to that line. So for every point on this line, where does y get greater? It gets greater going up. So I'm going to say, well, really, I'm talking about stuff up here. That's where y gets greater for this line. Now I'm going to do the other line in blue. Okay. Here my starting point is 1. So here's my 1. That's hard to get it right. And again, it's a 1, 1, except it's negative 1 over positive 1. So for every 1 I go down, I go over 1. For every 1 I go down, I go over 1, 1 down, over 1. So what I really have here is this line, okay? And again, it's greater than. So it's the stuff that's greater than all this line. So what I'm really concerned with is what is in both shaded regions. So I kind of have to just go through and say, okay, this has both blue and green shaded in it. All right, this little triangle and above. And that's what these arrows are kind of showing, and it goes forever. Okay, so that's how we graph some lines. Now in 21, it adds a level of difficulty in that they don't give us a y equals line. We're used to saying a y equals, or in this case, y greater than or less than. So I want to kind of move it around so it is a y equals line. So with this one, I'm going to start by saying, how can I move this to the other side? I'm going to move the x over here and make it a negative x. So technically, I'm going to just take it away from this side, and I'm going to move it to the other side. Now what I want to do is I want to divide each and every term here by 2. So in the end, my y is greater than or equal to 7/2 minus 1/2 x. All right, and I have to be careful. I have to realize that I kind of switched some things around. I'm going to do the same process here with this 3x. I'm going to move it over here. It's going to become a negative 3x. Get rid of it here. Then I'm going to divide each and every term here by a negative 4. So now my second equation becomes y, but what I did here is I divided by a negative. And with inequalities, that's like kind of my big rule. Whenever you divide by a negative, and that's kind of what I did there. I did each and every term I was divided by a negative. Here I was divided by a positive. It was a positive 2 everywhere. But now I divided by a negative. So now what I have is I have a negative 3 here, and then I have a positive 3/4 is my slope there. Okay? This 7/2, I'm going to think of it as 3.5, sorry. So let's graph the first one. Let's have our starting point. Our starting point is the constant, the one without the variable. So I'm going to think about that as 3.5. So 1, 2, 3.5. So that's about my constant. From my constant, I go my slope. I'm going to think of this as a negative 1 over a positive 2. So for every 1 I go down, I go 2 over. For every 1 I go down, I go 2 over. For every 1 I go down, I go 2 over. So you can kind of see this line. Now in this line, my y was greater than this line. So greater than goes above. Where does y go higher? Now I'm going to do my other line. I have a starting point here at negative 3. This has a slope of up 3 over 4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. All right, 1, 2, 3, 1, 2, 3, 4. Backwards I can go. And then this one, I have to go back through here in a minute. It was not necessarily just greater than or equal to, it was just a greater than. So I kind of have to do something to show, hey, it's not the line, but everything kind of near the line. So one thing I can do there is I can make it a dash line. So I just made it a dash line. And now it's everything above that still, because it's greater than. So we're going above now again. And then I'm going to go back through in red, and I'm going to highlight where is it both highlighted in red, and, or excuse me, in blue and green, and then I highlighted that in red. A lot of students just do that with kind of heavier markings on their their drawings. Here, this one, x is greater than or equal to 3. This one's a tough one. You have to say to yourself, if x was equal to 3, this is where x is equal to 3. These are all the lines where x is equal to 3. That's x equal to 3. No matter what y is, x is equal to 3. Greater than or equal to 3, or excuse me, less than or equal to 3. I'm going to show you here. I'm going to show you with some dashed lines here. So there's my dash lines. And things that are less than 3 is going to be over here. This is all the stuff less than where x goes smaller is on this side. In the other equation, I can just graph it like kind of we're used to. Here's my starting point at positive 1. It goes down 2 over 1, down 2 over 1 because the slope is 2 over 1. So here's my line, and it's greater than or equal to that, which is above. So now it's going to be in blue because that's what color I have left. Everything that's both less than that our x line or 3x equal 3 line, and yet greater than the other equation line. And that's going to be shaded in here. Okay? All right. And then we were looking at some word problems. I'm going to go ahead and pause it and make a second video.